Dear students, this is our 20th lecture on organic reaction mechanism, and today we will be discussing a few general aspects of reaction mechanism, in which we will be discussing potential energy level diagrams, then transition state and intermediates. Now as you know, in any organic reaction, we generally describe that reaction in terms of potential energy diagrams, and these potential energy diagrams they tell us that how reactants they are converted into products through intermediates, which in turn are formed through transition states. And each individual step in a reaction is accompanied by a transition state, and this transition state corresponds to the highest energy arrangement of the molecule in that step. So for example, if in this potential energy level diagram there are two steps, this is the first step where this is the highest energy arrangement, and here this belongs to one transition state, whereas here this is the second step and this is the highest energy arrangement which belongs to this transition state. And in between these two transition states there is a state which we call it as intermediate. And these intermediates, these are molecules that are formed, and then these intermediates they react further to get converted into products. If you see this reaction, when ethene reacts with HBr, we know in the first transition state, when they will come closer to each other, the energy will be highest, and when these two molecules they acquire this much amount of energy, that is energy of activation for first step, then we will have this type of arrangement where the HBr molecule will get attached to the carbon-carbon, start getting attached to the carbon-carbon double bond to have this type of transition state. And then when from this transition state this bromide tries to go as bromide negative, then an intermediate of carbocation, this type of carbocation and this type of anion will be formed. So these are the two intermediates, and when this transition state gets converted into these types of intermediates, then energy of the system become lower than the energy at this transition state. And then this intermediate that Br negative will interact with the this carbon positive, and we will have this type of transition state. And when this Br negative approaches this carbocation, then energy of the system will again rise. And if we compare with the energy, if we take this energy as 0, energy of the reactant, then this much of energy is required for conversion of a reactant into this transition state. This is the step 2 reaction, and energy required activation energy is EA2. And then this transition state gives us a stable product where the energy of system is lower than that of the energy of the reactant. So this much amount of energy is the energy difference between reactants and the products, and this is called as the free energy change associated with this reaction. So on the basis of this potential energy level diagram, we can tell about the various types of transition states involved in the reaction and intermediates which are involved in the reaction. Now if we see this, each steps 1 and 2 has its own energy barrier. As I have told you, the energy barrier for the first step is energy of activation of the first step, which is called as EA1, whereas energy barrier for the second step is EA2, which is activation energy for the second step. And if you see over here, EA1 is more than EA2, which means that step 1 is a slower step than the step 2. So therefore we know that slow step is the rate determining step. So in this particular reaction, that means step 1 is the rate determining step. So these are the various informations which we can get from these types of potential energy level diagram, and then we can know about the energy of activation for each step of the reaction, and whether the reaction will be spontaneous or not, or whether the reaction will be exothermic or endothermic. And in this case we can see that energy of the product is lesser than the energy of the reactants. That means this much amount of energy will be produced when reactants they are converted into products. So that means this type of reaction will be an exothermic reaction. If energy of the products is higher than the energy of the reactant, then in such case, in such type of reactions we have to give energy from outside to such products to be formed, and that type of reactions they are called as endothermic reaction. Now we will see few examples of different types of potential energy level diagrams. First is single step reactions. The most common example of single step reaction is SN2 type of nucleophilic substitution reactions. If you know that in such type of reactions, nucleophile attacks a molecule where we are having L is a leaving group, and in a single step the nucleophile will displace this leaving group, and we will get this type of product. And the attack of the nucleophile, as you know, in case of SN2 type of reactions, takes place from the back side of the reactant. And there is a point when nucleophile is getting attached to the substrate and leaving group is leaving the molecule, and such type of situation is this type of 5-membered transition state. So in terms of potential energy diagram, this is the energy when we are having both the reactants, they are approaching each other. That is, the nucleophile is attacking the alkyl halide, and when nucleophile approaches the alkyl halide, then this type of transition state is formed. And we know the energy at the transition state is highest. So this much amount of energy of activation is required for conversion of this reactant into this type of product. And you can see that here no intermediate is formed, only transition state is there. So this is an example of single step reaction. And again you can see over here the energy of the products is lower than the energy of the reactants, then that means SN2 type of reactions, they are exothermic in nature. Then two-step reactions, and the most common example of two-step reactions is nucleophilic substitution unimolecular, SN1 type of displacement reactions. And we know in case of unimolecular nucleophilic substitution reactions, in the first step the substrate changes into a carbocation and a leaving group anion is formed. And this step is a slow step, and because this is a slow step, that means this is rate determining step. And in the second step, the carbocation interacts with the nucleophile to give us the final product, and this is a faster reaction. Now we know that if this is the slow step, that means energy, potential energy for conversion of this into this will be higher than this fast reaction. So you can see over here the alkyl halide reacts with the nucleophile, and first we will have this type of transition state when the alkyl halide where X is leaving, this leaving group is trying to leave the substrate molecule, the energy of the system at this point will be highest. So this is the step 1, which is the slowest step, where this will get converted into a carbocation. So transition state is this one, and when carbocation is formed from the transition state, the energy will become lower. So and then this intermediate will again interact with the nucleophile to give us this second transition state, and this second transition state then will ultimately get converted into product where the nucleophile will get attached to the substrate. And you can see this is the first step of the reaction where first transition state is formed. This is the second step of the reaction where second transition state is formed, and these are where the energy of the system becomes lower. Then this is the first intermediate which is formed during the first step of the reaction. So this much of energy of activation is required for conversion of the substrate molecule into this transition state, and then this much is the change in energy, that is from intermediate to second transition state we require this much of delta G for conversion of this intermediate into this transition state, and overall the reaction is an exothermic reaction. Then three-step reactions are also there. Most common example is acid catalyzed rearrangement, which is also called as carbocation rearrangement reactions. So when we add say HBr acids to alkenes, then we get alkyl halides as the product with the addition of HBr to this carbon-carbon double bond, and we know that the addition of HBr will take place across the carbon-carbon double bond. So in such cases the first step is addition of H positive to the carbon-carbon double bond, and we will get addition of H positive to this carbon-carbon double bond will give us this type of secondary carbocation, and this formation of secondary carbocation means in the first step this will HBr will approach this carbon-carbon double bond, and a transition state will be formed where HBr is approaching this carbon-carbon double bond. This is a slow step. Then that transition state will get converted into this type of intermediate, and we know that secondary carbocations, they are less stable than tertiary carbocation. So there is a possibility of 1,2 methyl shift over from here to this place, and we will get a more stable tertiary carbocation, and this tertiary carbocation will then react with Br negative and we will get the product. This is a faster step, and first step is the slowest step, and as the first step is the slowest step, that means the energy of this step will be the highest energy. So this much of activation energy is required for conversion of the reactants, these two reactants, into the transition state where the HBr approaches the carbon-carbon double bond, and this will be your first transition state in the reaction, and this first transition state will lead to the formation of a secondary carbocation. Then this secondary carbocation, the shifting of this methyl will take place to give us tertiary carbocation, but transition state of in between conversion from secondary to tertiary will be our second transition state, where energy of the system will be highest, and that transition state will get converted into second type of intermediate. So this is first intermediate, this is second intermediate, that is secondary carbocation changes into a tertiary carbocation. Then tertiary carbocation will be approached by Br negative, and this will get converted into product. So when tertiary carbocation is approached by Br negative, then we will get this third transition state, and this third transition state will ultimately change into the formation of product. And you can see over here the energy of energy difference between the secondary carbocation and tertiary carbocation proves that tertiary carbocation is more stable than the secondary carbocation. So this is an example of three-step reaction. This is the first step, where the reactants, they get converted into an intermediate secondary carbocation. In the second step, secondary carbocations, they get converted into more stable tertiary carbocations with 1,2 methyl shift. And in the third step, the tertiary carbocations, they are approached by Br negative to give us the product. So this is an example of three-step reaction or carbocation rearrangement, which is catalyzed by acids. Then, as I have told you, exothermic and endothermic reactions. So where the energy of the product is lower than the energy of reactants, such type of reactions, they are called as exothermic reaction. And if the energy gap between these two is high, the delta H value or delta G value is larger, then such type of exothermic reactions, they are called as irreversible exothermic reaction. Similarly, if this value is high in case of endothermic reactions, then also such type of endothermic reactions, they are called as irreversible endothermic reaction. And in case of endothermic reactions, the energy of the products is higher than the energy of the reactants. That means we have to supply this much amount of energy to the system for the reaction to get converted into the product. Similarly, reversible exothermic reaction and reversible endothermic reactions, the difference between the energy of the reactant and products is small. So if it is smaller, then such type of exothermic or endothermic reactions, they are called as reversible exothermic reactions or reversible endothermic reactions. So in conclusion, the thermodynamic stability will determine the relative energy of reactants and products, but this does not provide any information about the intervening stages. That means intervening stages means the transition state and the intermediates. So these intervening stages will determine that how fast or how slow the reaction will be, because as you have seen in case of transition state, different transition state have different value of activation energy. Higher the amount of activation energy, slower will be the reaction. So if the large delta G, that means more amount of energy of activation is there, If large delta G is required, that means the reaction will be a slow reaction. And as I have shown you that the reactions they proceed through a sequence of steps, and each step is having an intermediate which is formed through a transition state. And the sequence of these reaction steps and intermediate involved in overall transformation of a reactant into a product is called as reaction mechanism. And reactants, intermediates and products, they will correspond to energy minima in the energy level diagram. So reactants, they will be shown at a minimum energy. Intermediates, they will also be shown at a minima of energy, and products will also be shown at a minima of energy in the energy diagrams. And these reactants, intermediate and products, they are separated by activated complexes or transition state. And and you have seen in the previous slides also that transition states, they are shown as the having maximum energy for each successive step of the reaction mechanism. Thank you very much.